Good morning. Today we are going to see lecture 27, equivalent circuit of single phase induction motor. And the main purpose of this equivalent circuit can be developed by double equivalent field theory, as well as the equivalent circuit will consider standstill as well as running condition. Okay. And also equivalent circuit applicable to load test, that is no load test and blocked rotor test. And when we are doing the blocked rotor test, okay, when we are doing blocked rotor test, the induction motor will act as transformer with its secondary winding secondary winding short circuit. Short circuit, secondary winding short circuit. Okay, now I'm going to draw the equivalent circuit of a single phase induction motor at a standstill. Okay, first diagram. Figure 1 denotes equivalent circuit of single phase induction motor at standstill. Okay. Now for this we are having two terminals, positive, negative. Okay, and for this terminal we have to apply the voltage V. Okay, for this positive negative we have to apply the voltage V, and once you give the voltage, then it will be connected to the stator. Okay, it is connected to stator. Stator is having winding. Okay, and the notation here for resistance R1, the reactance X1. Understand? So R1 V is the terminal voltage, that is single phase AC. AC. Then if you give the voltage, the current flows. The current is I1. Okay, so I1 is the stator current. Stator current. Okay, and the combination of this R1 X1, call it as, is a stator. Okay, so this is stator. So R1 is the stator resistance, X1 is the stator reactance. Stator reactance. Okay, then it will be given the stator winding. It is connected with the a leakage, magnetizing resistance and reactance to find out the losses. Magnetizing resistance magnetizing reactance. This is nothing but Rm Xm. Rm stands for magnetizing leakage resistance, and Xm is the magnetizing leakage reactance. Leakage reactance. The current flows, because this is my terminal, the current flows in this magnetizing part, that is nothing but I M. Okay, IM stands for magnetizing current. Magnetizing current. Now, afterwards, the current will be entering into the rotor. Rotor is having resistance and reactance. Okay, resistance and reactance. The notation here R2 dash. This R2 dash stands for rotor resistance. Okay, and X2 dash stands for rotor reactance. Okay. And the current flows in the rotor I2 dash. This I2 dash stands for rotor current. Okay, and the flux produced in leakage that is EM. EM stands for EMF induced in stator. Okay, EMF induced in the stator. Now here you see this diagram. This is the rotor, stator R1, and this part, right hand side, this portion rotor. Okay, rotor. Understand? So the supply which we are giving, it will be single phase supply omega t volt 220 volt 50 hertz single phase supply. Understand? This is a figure 1 for equivalent circuit of single phase induction motor at standstill. Standstill means it is not running. Okay, it is not running. It's not running. You understand? Now, figure 2. Figure 2 shows equivalent circuit of single phase induction motor under normal operating conditions. Normal operating conditions means it is running conditions. Okay, it is running conditions. Now in single phase, once the motor will be start running, it will be create a rotating magnetic field in both forward as well as the backward. Now this diagram will explain how to represent this forward and backward in equivalent circuit in terms of winding arrangement. Okay, so the same procedure, plus minus the supply which we are giving B voltage. Okay, so once you give the voltage, the current flows in the stator, that is I1. Okay, and afterwards it will be given in the stator. R1 X1. Okay, R1 X1. Then it will be given to a leakage arrangement arrangement, that is Rm Xm, but we have to represent this into two. Okay, into two portion, one for forward, another for backward, another for backward. Okay, forward, another for backward. This line shows it will be a topmost top point is applicable for forward field, this bottom portion applicable for backward field. So value will be equally divided, Rm by 2 Xm by 2. Here also Rm by 2 Xm by 2. Understand? And the resistance value will be available at standstill. Since the motor it is in standstill, we have to represent. Okay, this is R2 dash by 2 X2 dash by 2. Okay, R2 dash by 2 X2 dash by 2. So it's not running, right? Okay, it is in standstill. Okay, now it is in standstill. So here I am representing it is in standstill. Okay, it is in standstill. So this portion r2 dash by 2 x2 dash by 2, and the current flowing here, it is in magnetizing Im F, and here it is Im B, and the current flowing in the rotor, it is rotor current I2 dash, it is forward. Here also I2 dash backward. Okay, and the flux, sorry, the EMF produced here, it is the notation EMF. EMF equal to total EM divided by 2. Okay, like that. Here also EM B equal to EM by 2. EM by 2. Okay, so this method which we are representing in forward and reverse field, will call it as this double revolving field theory. Okay, double revolving field theory. Now by using this theory, we are separated, okay, we have separated the magnetic fields in terms of two. One is forward, another one is backward. Okay, now figure 3, figure 3 represent equivalent circuit of single phase induction motor under normal operating condition. Normal operating condition means running. Here I'm going to run the motor. Okay, it is running condition. Now in running condition, now by using this figure 2, now again I'm going to rechange, okay, rechange this diagram. So what I'm going to do it here, in running we have to adjust only the rotor resistance parameter. Okay, rotor resistance parameter, that parameter which we are representing plus minus V, which will be given to R1 X1 I1 stator current. Okay, then it goes to here leakage, magnetizing leakage resistance and reactance, because I already mentioned this, you have to divide the diagram into two, and this topmost point called as forward field, downward call it as backward field. Okay, so this is Rm by 2, this one is Xm by 2, which is connected. Again, Rm by 2, Xm by 2. Okay, the current flowing here, it is Im F, here it is Im B. Okay, and the EMF induced EMF equal to EM by 2. Here EMB equal to EM by 2 in backward. And the load they are taking resistive and inductive. Resistive and inductive. The notation R2 dash divided by 2 X2 dash divided by 2. Okay, since the motor is running, so by varying the resistance, so it will be resistance, the resistance value will be vary. Okay, it will be vary based upon the variation, the resistance will be value will be vary. So how much it will be vary means R2 dash by 2 into S. Okay, R2 dash by 2 into S, it will be vary. Okay, the variation here, it is the speed will be vary S with respect. Okay, the sleep when motor is running at a speed of n with respect to forward field, the slip S with respect to forward field. Okay, in forward field, slip S will be considered when motor is running. Okay, in backward, when motor is running, original I don't have no sir. First year I have sir. First year all the things I have sir. Slip will be vary from 2 minus S with respect to backward field. The original you only will blame no sir. They like there no hiding you. Auto dash by 2 into instead of S I am putting 2 minus S. X2 dash by 2. Okay, only variation in resistance. You see, in forward it is R2 by 2 into S. In backward R2 dash by 2 into 2 minus S. And the variation here in resistance. Okay, the variation here it is in resistance. The current flowing here, it is I2 dash, since it is applicable for forward, I2 F dash, like that here also I2 dash suffix B. Okay, backward. Okay, this I2 dash F notation called rotor current in forward position. Okay, I2B dash called rotor current in backward field. Okay, in backward direction. You understand? Okay, now when you see this diagram, in leakage there are two types of loss are there. Okay, in leakage there are two types of loss are there. in leakage, magnetizing effect. Two losses are present. Okay, so the loss, core loss, produced in Rm by 2 and and hysteresis losses, hysteresis losses, or we can say it will be a be taken as rotational losses also. Okay, we can say it will be a rotational losses. Xm by 2. Okay, now the figure 4 shows equivalent circuit of single phase induction motor under running condition by neglecting core loss. The other name of core loss is copper loss. Okay, what you have to neglect? We know that core loss means Rm by 2 we have to neglect. So the diagram which we are going to draw without having core loss. Plus minus V R1 X1 stator. The current flowing here, it is I1 input current. Okay, now it goes to this terminal. It is having two parts. Okay, the topmost part is forward, field. Backward part is downward part is backward field. Okay, so we have to neglect Rm by 2. So the leakage, magnetizing leakage reactance, I am drawing only this, only Xm by 2 is available. Okay, Xm by 2 is available. Xm by 2 is available. Okay, so the current flowing here Im F, here Im B. Okay, and the EMF produced here, EMF in forward, EM by 2, in backward, EM B equal to EM by 2. Okay, EM by 2, EM by 2. Now we have to draw the load. Okay, load, that is nothing but resistance, reactance. This is nothing but R2 dash divided by 2 into S. This one X2 dash divided by 2. Okay, so the connection from stator, which will be given to the rotor current resistance R2 dash. The current flowing here I2 dash F, I2 dash F, like that. Here also the same, it will be connected to a resistance. To a resistance. So the notation R2 dash by 2 into 2 minus S here X2 dash by 2, and the current which will be connected here. Okay, so the current will be flowing here I2 dash B, I2 dash B. So this is the equivalent circuit of single phase induction motor in a running condition by neglecting core loss. Okay, by neglecting the core loss. Now I am going to explain and how to draw the equivalent circuit for testing conditions in terms of no load and blocked rotor. Okay, yeah, induction motor is applicable. Single phase induction motor equivalent circuit can be drawn by using two tests. One is no load test. Second one blocked rotor test. The other name of blocked. The slip value for no load test here S equal to the slip value which we are setting for no load test S equal to 0. For no load test S equal to 0. For blocked rotor we have to set S equal to 1. Okay. s equal to 0, s equal to 1. Okay, so we know the slip s equal to ns minus nr by ns. If you substitute s equal to 0 in this equation, we can get ns equal to nr. Okay, ns equal to nr. Okay, in no load. In block rotor, what happened? When you substitute s equal to 1 in the above equation, you will get s ns equal to ns minus nr, then nr equal to ns into 1 minus s, which we are getting. This is the difference. Okay, this is the difference. Now by using this s equal to 0 in no load test, I am going to draw an equivalent circuit. Okay, so figure 5 shows equivalent circuit of single phase induction motor for no load or no load test. Okay, so here the same thing, plus minus, you are giving voltage. Okay, and to measure here it will be R1 X1, and the current flowing here it is I1. This is stator. Okay, the current flowing here it is I1, and and it is given to because we are just eliminating, note down, we are eliminating 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 the magnetizing losses. Magnetizing losses, that is Rm by 2 we are eliminating, and Xm by 2 also eliminating. Okay, we are eliminating both. So the load value for this one will be R, sorry, we are eliminating the core loss. Okay, we are eliminating the magnetizing losses, only core losses we are eliminating. So here I am drawing only the core loss, it is Xm by 2, and in resistance value, because in forward there will be, in forward and backward there will be a formula R2 dash by 2s, here X2 dash by 2. Okay, now here you see in forward, okay, this is a forward, this is a backward. Okay, now here when you see in forward this, if you substitute s equal to, because we know the condition of no load test, s equal to 0. If I substitute s equal to 0, I will get r2 by 2 into 0, I will get infinity. So better you we can avoid this term. Okay, we can avoid this term because since it is, we are getting infinity parameter. So in backward there will be resistance and reactance parameter will be there. That resistance will be r2 dash by 2 into 2 minus s. Now if I substitute s equal to 0, I can get r2 dash by 2 into 2 minus 0, I can get r2 dash by 4. So therefore, okay, therefore I can eliminate this term, I will erase it, then I can write r2 dash by 4 like that. X2 dash by 2, it is already, it will be there. Okay, it is already, it will be there. Are you understand? You understand? Okay. And this is the equivalent circuit. The current flowing here, it is Im. Okay, Im, and here it is flowing here I2 dash B. Okay, I2 dash B. Okay. So this is the equivalent circuit of single phase induction motor for no load test. In terms of blocked rotor, figure 6 shows equivalent circuit of single phase induction motor for blocked rotor test. So in this method, we have to take positive, negative, V, X1, then it is given to, because in block rotor we will eliminate all the losses. Okay, note down, eliminate losses, Rm by 2, Xm by 2, Rm by 2, Xm by 2. So we can write here R2 dash by, here we have S equal to 1, so R2 dash by 2, and here X2 dash by 2. Here R2 dash by, R2 dash by 2, here X2 dash by 2. The current flowing here, it is I2 dash, here it is I. Okay, this is the block rotor test. So to find measure the voltage, we can connect ammeter here, and if you want to measure the terminal voltage, you can connect voltmeter here. Okay, because anyway in block rotor we have to use one voltmeter to measure ESC, ammeter to measure ISC, power using wattmeter to measure WSC. So these three apparatus which we are going to use in this block rotor test for measuring purposes. This diagram is one of the easiest concept to measure all the performance parameters are available in single phase induction motor.
No, in my home it was only in front I took care. And this one and all I want to search it will be somewhere else. That's it. Ah, she's here only.
You started in the house.
That's my online class in progress now. You know the components only you are studying. You have to keep the components. And we are only first he told you will do partition, but somebody against nobody is coming for this thing. We are partitioning in this thing money. For that we have to invest 1.5 lakhs.
Okay. Now we are going to draw. We are going to do a problem which is available in the text. Okay. A 220 volt, a 230 volt, 230 volt, 4 pole, 50 hertz, single phase, 50 hertz, single phase induction motor has an effective rotor resistance and leakage reactance of 0.5 ohm and 5 ohms. Respectively. It is running at a speed of 1350 rpm. Determine a frequencies of forward and backward rotor current component. second subdivision, frequencies and impedance, and say it's impedance also, frequencies and impedance. Okay, P part will be relative magnitude of current, relative magnitudes of forward and backward fluxes. Neglect magnetizing current and stator impedance. Stator impedance means it is Rn by 2, Xn by 2. Okay, this is the problem. Now we'll solve the problem. First, solution. Okay, solution. In solution, we have to write here. First, find out the frequency and impedance of forward and backward. What is my first step? Frequency forward rotor frequencies of forward rotor current. The formula for this, F rotor means dash. Okay, F dash frequency F dash stands for rotor. Since it is forward, right? F. Okay, F dash F equal to slip S into Fs. Okay, S into Fs. We don't know the Fs value. Fs we know, but slip value it is not available in the problem. So how to calculate the slip? We know that S equal to Ns minus Nr by Ns. Nr which is available here, Nr value will be 1350 RPM. Okay, but we don't know Ns. So Ns is equal to 120 Fs by P. Now substitute 120 into Fs how much? 50 divided by number of pole here it is 4. You will get 1500 RPM. Okay, that is Ns. This value substitute here. 1500 minus 1350 divided by 1500. We are getting 0.1. Okay, this is slip 0.1. Now this value substitute 0.1 into Fs how much? It is 50 supply frequency. It is 5 Hertz. Okay, the next frequency of next one frequency of backward rotor currents. The notation frequency f, it is a rotor f dash b. Okay, here in forward it is rotating with slip, yes. In backward it is 2 minus s. Instead of s I am substituting 2 minus s into fs, which is equal to 2 minus s value we already got it, 0.1 substitute into 50 into 50, you will get 95 hertz. Okay, 95 hertz. Next, impedance also we have to calculate. Impedance means z. Impedance of forward rotor current. Okay, so in the diagram, you know, in forward there will be, in forward it is R2 by 2s, this is S2 dash by 2. Okay, the current flowing here it is I2 dash f. Okay, this is for forward, right? Forward. So the combination of these two, okay, I can write R f plus j x f. Okay, f stands for forward. So the notation for impedance z f equal to, we know the impedance formula, summation of resistance and reactance. So Rf plus jx f. Okay, so which is equal to, what is Rf? R2 dash by 2 s 2 s plus j into this xf means x2 dash by 2. Okay, now substitute R2 dash, as per our given data, the R2, okay, R2 dash will be, R2 dash will be dashes, here it is 0.5, x2 dash is 5. Okay, that we can write it here, that we have to write it. So as per your, in the problem itself, we know that from problem given data, R2 dash is 0.5 ohms, 5 ohms. This we can substitute 0.5 divided by 2 into slip value, it is 0.1 plus j into x2 dash is 5 divided by 2. We can get 2.5 plus j 2.5 ohms. Okay, if we represent in terms of polar form, it is 3.536 angle 45 degree ohms. Angle 45 degree ohms. Okay, in the similar manner, we have to write impedance of backward rotor current. So the formula ZB, ZB equal to RB plus JXB, which is equal to, what is RB? Because in backward, what is the, how it will be represented? This is R2 dash by 2 into 2 minus S. Here x2 dash by 2, x2 dash by 2, and the current flowing here it is I2 dash B. This is for backward. Okay, this RB is the backward resistance. Backward resistance value will be R2 dash by 2 into 2 minus S plus J. XP is backward reactance, x2 dash by 2. Okay, now in this formula substitute it. R2 dash 0.5 divided by 2 into 2 minus slip is 0.1 plus J x2 dash 5 divided by 2. We can get 0.1316 plus J 2.5 ohms. If we convert into polar, 2.5035 angle 86.99 degree ohm. Okay, 99 degree ohm. Okay, then we will go to second substitution. What is our second substitution? We have to calculate the relative magnitudes. Relative magnitudes of forward and backward fluxes. The flux notation, it is phi F divided by phi B, which is equal to EF by EB. Okay, EF by EB. So we know the basic impedance equation with respect to EMF. Z equal to ratio of EMF divided by current. So from this, induced EMF E equal to product of impedance and current. This equation we can substitute here. ZF into IF whole divided by ZB into I. Okay, into IP. So in both the cases, IF and IB, that's not right. Okay, so because in both the case, this current is same because we are giving the same stator current only. So it is I1 ZB into I1. So we have this I1 will be cancelled. So finally we'll get ZF and ZB. So what is our ZF? ZF value which we already calculated, right? So here 3.536 angle 45. 3.536 angle 45 degree 4 divided by ZB is 2.5035 angle 86.99. Okay, since we are going to calculate as per our question, we are calculating only magnitude, so we should not bother about the angle. So we are calculating only magnitude, only magnitudes. Okay. Magnitude means we have to consider only this portion. Okay, we have to consider only this portion. So we'll get 3.536 divided by 2.5035. So finally we'll get 1.4. Okay, so therefore the relative magnitudes of flux phi f divided by phi b, which we are getting 1.4. 1.4. Okay, thank you.